The purpose of this example is to give you an introductory, just look at a very simple case of boundary conditions so that for dielectrics, between two dielectrics, so that you can get a feel for what it means and build a little bit of intuition. We're given two regions. One is 5 epsilon naught on one side, and the other is 4 epsilon naught on the other. This boundary is the z-axis, so this is z equals 0, and one of the ways that this problem is looking a little bit, very, very slightly tricky is that it's a 2D problem, but instead of x and y, you're having the z-axis be one of your axes of interest. All right, so in this case, this is the z-axis, and with this is we'll draw this as the x direction, and we're given an electric field E1. Actually, I should draw it in a direction that bears some resemblance to the way it's listed. So E1 is going to be 2 E naught of x hat plus z hat. So if you were to look at the direction from the normal vector, this would be what's the angle here? Yep, 45 degrees, right? And the question that you're given is, well, what is it on the other side? So over on the other side, you're going to have an E2, and you want to know what that is. So this is a quick review of this is our normal vector. A quick review of conceptually. I want to just minimize the math so that we can just focus on conceptually what happens. But the key concept for boundary conditions is that the tangential field, so the field that's parallel to the interface, is going to be continuous. So in this case, that means that EX1, the x component for E1, is going to be the x component for E2. Right? Therefore, I would say E2, we'll just call this the tangential component of E2, is going to be equal to 2 E naught x hat, right? Or let's take this a step back. So when we're looking at this, we can break this down into a normal component and a tangential component. Right? And in this case, the tangential component, since the normal component is in the z direction, the tangential component is going to be 2 E naught x hat, and the normal component is going to be 2 E naught z hat. So here we're given the result for the tangential component, and in the case of dielectrics, the normal component, electric flux density, minus the difference between electric flux density normal components for the two interface is going to be the surface charge density. In the case of dielectrics, none of the charges can move, and so with the exception of the boundary being drawn to completely split an atom, so to speak, the surface charge density on a dielectric should be 0, which means that when you're solving for dielectrics, the electric flux density is continuous. And therefore, epsilon 1 E1 normal component is going to be equal to epsilon 2 E2 normal component. And we saw that the normal component is 2 E naught, and it's in the z direction. And epsilon 1 is going to be 5 epsilon naught. So we have 5 epsilon naught, 2 E naught is going to be, and then over here we have 4 epsilon naught E2 normal. And just keep in mind that this is in the z direction. So the normal direction is the z direction. Now we can go ahead and solve for this. The epsilon naught part cancels. So the normal component of E2 is going to be, so these two cancel out to be 2. We're going to get 5 over 2 E naught z hat. So now you can combine these two together, and you'll know that the electric field in region 2 is going to be equal to 2 E naught x hat plus 5 over 2, or 2.5 E naught z hat. And that is going to be the electric field on the other side. Now the one thing that let's just also kind of just qualitatively look at it and see how it compares to the normal. So on the other side of the electric field, the tangential component didn't change. But what happened to the normal component? Sorry, the normal component did it increase or decrease? It increased, right? So if I were to exaggerate, the vertical part stayed the same, but the horizontal part, which is the normal component, decreased a little bit. So the light bent this way a little, right? So the main thing I wanted you to just see is, is this greater or less than 45 degrees? It ends up being slightly less than 45 degrees, right? So the direction of the electric field changed because, again, the tangential component doesn't change, but the normal component changes if you're moving from one permittivity to another. And that is the reason that the electric field will bend if you're going from one medium to another. And another key important thing is, and you're not coming straight on at it, right? So if you're coming straight on, the field won't change because there's no kind of differentiation between the two components, the normal and the tangential component. But if you're off the normal by any amount, you're going to get some slight change in the angle. And this phenomenon, this boundary condition criteria, is how we end up with Snell's law and light refraction, where you see the light bending as you go from one medium to another. And so to review, I think the main thing is I just wanted to further reinforce how you go about boundary conditions when you go from one medium to a next. The first rule is that the electric field is continuous in the tangential component. And the second rule is that the electric flux density, any kind of difference, results in a surface charge. And in the case of a dielectric, the surface charge is 0. So for a dielectric, you get the rule that the electric field tangential component is continuous and the electric flux density is continuous in the normal direction.